Our next presenter this morning is Silas Tanner from the GTM Research Reserve.
My name is Silas Tanner. I'm the System-Wide Monitoring Program Technician at the GTM Research Reserve. Today I'm going to be talking about some of the research that I've been conducting over the last few years, refining techniques for high-frequency monitoring of chlorophyll within the national. So we've heard a lot this morning about why we measure chlorophyll and its importance for water quality monitoring. It gives us a proxy for the nutrients within our waterway, as well as a proxy for the phytoplankton abundance. So our system-wide monitoring program is required to measure chlorophyll monthly via extractive analysis of the discrete water samples that we take at our long-term monitoring sites. However, we know this process can be slow and labor-intensive, and oftentimes we don't receive the results of our monthly water quality sampling for up to 3 weeks following our collections. But what about the short-term variability of our system? The system-wide monitoring program is focused on monitoring both the short-term variability and the long-term change within our estuary. But however, we know that phytoplankton dynamics, they can fluctuate hourly based on a laundry list of abiotic and biotic regulatory processes, such as sunlight, winds, tides, water color, nutrient availability, grazing by other organisms, just to name a few. So YSI, or Xylem YSI, the manufacturer of the data sondes that we use within the system-wide monitoring program, has developed an optical sensor to monitor chlorophyll fluorescence in situ or within the environment. So using the EXO data sonde allows for the capability to pair chlorophyll monitoring data taken every 15 minutes with a whole suite of abiotic parameters such as temperature, salinity, dissolved oxygen, pH, turbidity, and the fluorescently dissolved organic matter that Shannon mentioned. So implementing the sensor into the SWAMP program provides a rapid and autonomous way of monitoring chlorophyll fluorescence. These sensors are intended to complement monthly discrete sampling efforts in an effort to paint a better picture of the temporal variability of our estuary. So here's a time series of data that's been collected since we implemented the sensor into our monitoring program. And this data is specifically from our Pellicer Creek station. The gray circles on this graph represent the 15-minute chlorophyll fluorescence data. And the yellow circles and blue circles represent our discrete water samples from our automated water sampler and our grabs. So here's a close-up of the 2020 year. The green circles in this graph, they do represent the chlorophyll fluorescence data. And then the blue and the yellow circles are the same as the previous graph. They represent our discrete water quality extractive samples. And so as Shannon and Nikki mentioned, all this data is publicly available. And here I've actually plotted two axes on this graph, kind of to kind of paint the picture that however the sensor is measuring chlorophyll in situ, it's based off of the fluorescence of the molecule. Whereas when we get our chlorophyll data from the labs, that's based off of extractive analysis in which the cells are lysed and the chlorophyll is actually measured from outside of the cell. So I like to say, I mean, we're still comparing apples to apples, but they're different kind of apples. You know, I like to say a Red Delicious versus a Granny Smith. Some are better for eating, others better for baking pies. So however, we can see that there is some generally good agreement between the sensor and extracted chlorophyll measurements. However, there's some points in time where we see these data sets become decoupled. And so we're kind of wondering what may be leading to this. So I provided a close-up of the data collected in April of 2020. And I did this just to kind of paint a better temporal picture of the data that we're getting from the sensor and kind of what it can show us. So here we can see that our discrete sampling efforts did a pretty good job at catching some of the variability in chlorophyll biomass at the site. However, we can see that there was a point in time earlier in the month which showed greater and much more prolonged chlorophyll through the eyes of the in situ sensor. This increased and prolonged duration of increased chlorophyll would have been missed without the high frequency sampling that the chlorophyll fluorescence sensor provides. And so I previewed this research last year during last year's State of the Reserve as a poster presentation. The poster was intended to define the project objectives, detail the experimental methods, summarize the research significance, and then provide some preliminary results. So in this presentation, I'll be diving deeper into the data that was collected during the project period, and then discussing some of the conclusions that we came to. So how do we know that these sensors are accurate? This is actually a picture of me asking myself that question. So our fundamental research question was, is there an empirical or validatable relationship between in situ chlorophyll fluorescence monitoring and traditional extractive chlorophyll measurements. Furthermore, the project objectives included assessing the sensor's reliability across a wide range of environmental conditions, identifying any interferences that may lead to inconsistencies within the data collected by the sensor, and then furthermore, developing recommendations for the NERRS system regarding inclusion of the sensor within the SWAN program. And the ultimate goal was to develop estuary or condition-specific relationships between the chlorophyll monitoring data coming from the sensor and extractive chlorophyll measurements. So here's a figure that diagrams how the sensor is emitting a specific wavelength of light targeted toward our pigment of interest, which is chlorophyll A. And so this chlorophyll pigment gets excited by this blue light and fluoresces the red light to dissipate some of this photic energy, which Gabby mentioned in a previous presentation. And so this fluorescent red light is therefore detected by the sensor and then quantified to give us an output. However, the presence of quenchers, or these absorbent molecules denoted in the figure, lead to inconsistencies between data collected by the sensor and maybe data that would be provided by true extractive analysis. These quenchers can either scatter or absorb the light emitted by the sensor, either before or after the chlorophyll molecules are excited. And so this fluorescence data is intended to be validated through paired sampling with traditional extractive analysis in order to determine the presence of any interferences influencing these sensor outputs. And so to define our experimental hypotheses, our null hypothesis is that the chlorophyll fluorescence sensor data does not correlate with the extracted chlorophyll concentrations. Our primary hypothesis is then that the chlorophyll data does correlate with the extracted concentration of chlorophyll within the water. However, we've got a couple of additional hypotheses. We can see that there's a secondary alternative hypothesis that the sensor does correlate with the extractive values. However, this relationship can be improved by incorporating some of the data that the accessory data that the data scientist is collecting simultaneously. And then our tertiary hypothesis is just a reiteration of our secondary hypothesis to include some of the potential interactions between these interferences that are noted in the literature. And so I focused my sampling efforts for the project at the Port Palliser Creek Station, as this site is very highly dynamic and, as Nikki mentioned, is unfortunately impaired for chlorophyll. And so we employed two different collection methods, both intended to sample the same water mass with the sensor and extractive analysis. So using our automated sampler seen here on the left, the field-based method collected 1 liter samples hourly over a diel or 24-hour period. The second collection method was using dark Nalgene carboys in order to collect sample water to return to the lab for processing. And I put a picture of Palliser Creek right here just to denote that all the data collected for the project was at the Palliser Creek Station. And so once collected, sample water is filtered, extracted with acetone, and analyzed on a benchtop fluorometer, similar to the extractive analysis that is done with our monthly SWAN samples. The laboratory-based sampling here shown on the right involves transferring the collected water from the carboys into this darkened mixing tank placed on top of a magnetic stir plate with the data sonde lowered inside. And then the sonde is actively monitoring chlorophyll while the samples are drawn from the tank for extractive analysis. So here's a scatter plot of all the data that was collected from all of the 12 reserves around the nation. Initially there was hope for a global relationship between the sensor and extracted values, but as you can see here, the extracted data only trained about 35% of the chlorophyll fluorescence data coming from the sensor. So utilizing a model building approach, we were able to improve this relationship from up to 65%. So now only about 35% of the variability in the extractive data is not explained by the sensor data. Temperature, turbidity, and fluorescently dissolved organic matter were all significant additions to the model and improved the fit of the data to the regression line. And as mentioned before, there was a possibility for interactions amongst the interferences, and we did see that in the data that was collected. So here I've color-coded the data by the reserve and symbolized by the collection method. Our data is the olive color, which is down here extremely below the regression line. And that means that the chlorophyll sensor was overestimating the actual amount of chlorophyll within the water via extractive analysis. However, not surprising that reserve was a significant addition to the model, because there's a great amount of variability that could be attributed to differences in location around the nation. And season was also a significant model addition parameter. Again, not surprising, as we know that phytoplankton growth is dependent on sunlight availability, which we know changes throughout the year. So here, just focusing on the data that was collected at the GTM. Again, all this data was collected at our Pellicer Creek station. The initial regression analysis shows that about 61% of the variability in the extraction data is able to be explained by the sensor. However, using the model building approach mentioned before, we were able to improve this coefficient of determination to about 80%, leaving only about 20% of the variability within the data set unexplained. So we know that temperature, turbidity, and fluorescently dissolved organic matter are all significant additions to the model. So we need to test to what extent these interferences affect the sensor output. How to test the interactions between the interferences is still under investigation. So here I've shown, I've tested the effect of increasing turbidity on the sensor's chlorophyll fluorescence output. So we needed to serially increase the amount of the concentration of suspended solids and note the resulting response from the sensor. So on our graph here, on the x-axis, I have the turbidity, or the amount of suspended sediment within the water. And then on the y-axis, I have the chlorophyll sensor readings in RFU. So I ran 2 trials using combusted marsh sediment, both resulting in a linear negative correlation between chlorophyll fluorescence and turbidity. Efforts were made to test the theoretical expected range of turbidity seen within our estuarine environments up to about 1,000 FMU. Furthermore, I tested the effects on increasing fluorescently dissolved organic matter on the sensor's chlorophyll fluorescence output. And the way they did this was, again, serially increasing the amount of dissolved organic matter and noting the resulting response from the sensor. So multiple FDOM surrogates were tested in order to observe the relationship between carbon source and the sensor response. So in addition to the surrogate that I produced, which is here in the middle on the figure, or sorry, on the picture on the left, North Inlet Winyah Bay and Lake Superior National Estuarine Research Reserves both provided FDOM surrogates to be tested. In addition to these homemade DOM surrogates, I also tested a commercially available humic acid, just to see the result of that single fluorescent species on the sensor output. And so I ran 4 trials. I know this figure is a little messy. I ran 4 trials, 3 of which resulted in a positive linear correlation between fluorescently dissolved organic matter and the sensor output. And again, efforts were made to test the theoretically expected range of dissolved organic matter within our system up to about 200 QSU. So again, we can see here that not all FDOM surrogates are created equal, which goes to show the importance of considering your FDOM source on the sensor's output. So circling back to our hypothesis testing, we did show the presence of interactions between the interferences, eliciting further investigation into the variability of these influences. Furthermore, it is interesting to note that the global model is likely not feasible because the addition of reserved into the model explain more variability than any other addition. So what does this all mean? So we must understand that, again, the extractive analysis is very different than fluorescence monitoring. Oftentimes, how pigments behave in situ or within their environment is very different than once they've been extracted from their cell. So we've developed a rigorous methodology to help field calibrate these sensors beyond the manufacturer's protocol in an effort to better predict the extracted chlorophyll biomass within a water using chlorophyll fluorescence on a site-by-site basis. So again, we applied this model building approach in an effort to increase the predictive capabilities of the sensor. And one of the major advantages of using this sensor is the ability to incorporate the other sensor parameters collected concurrently to aid in data interpretation. We determined that turbidity and fluorescently dissolved organic matter were the most significant additions to the model globally. And furthermore, the variability within the FDOM interference elicits further research into the effect of varying dissolved organic matter on the sources of the sensor response. So not all dissolved organic matter is created equal in the eye of the sensor. And then finally, data with low temporal resolution is often very difficult to interpret. By supplementing our current discrete sampling efforts with high frequency chlorophyll monitoring, we deliver greater insight into our dynamic S-stream system. Thank you. And I've provided a QR code here. If anyone's interested, this will take you to our project page, which outlines some more of the background of the project. And with that, I'll take any questions.
Great, thank you so much, Silas. And thank you for sharing that QR code. I'll actually keep your screen up instead of advancing to your headshots. That way folks have a moment to scan that QR code.
Great.
And we do have time for questions if anyone would like to share questions in the chat box or raise your virtual hand. And I've got a question to kick us off, Silas. How do you think, with all the data that you have collected with this project, how do you think this might change monitoring at the GTM Research Reserve?
I think that implementing these sensors has really given us like I said, a greater insight into how dynamic our S-stream variability is. I really like looking at how, when we've got these passing showers that come through in the summertime, we can really see, the influence of that rainfall on our S-stream systems, at a near real time manner. Using the telemetry site from our Pellicer Creek station, I can go on and check every hour, check and see what the data is doing hour by hour. So it really gives us a finger on the pulse of the estuary in almost near real time.
Do you think you might implement these sensors in additional locations?
Yeah, so we've got the sensors at all 4 of our system-wide monitoring program locations, and Olivia also has one deployed at the Michler site as well. So pretty much wherever we've got a data sonde in the water, we've got a chlorophyll sensor on there. So yeah, we're definitely all on board. We just need to do a little bit more research into the comparing the extractive values against the fluorescence data.
Great, thank you, Silas. Are your sensors recalibrated, and how do you test for accuracy?
Yeah. So our sensors are recalibrated about every 2 to 3 weeks. In the wintertime, I can kind of get away with about 3 weeks due to the less biofouling in the water. But yeah, the sensors are calibrated using a rhodomine standard, which is again standard amongst the protocol, which is given by the manufacturer. And after bringing the data sondes back into the lab, I place them into deionized water to see if they can track any sensor drift that may have occurred. However, these sensors, since they're optical sensors, they're not really prone to any optical drift. So they are pretty reliable amongst the whole deployment.
Great, thank you. Would you be able to give some information on the cost of the data sonde versus the extraction method? Sure.
Yeah. I mean, so the price of the extraction method is going to vary between labs. The sensor is about $3,000. So I mean, it depends on the longevity that you're going to get out of the sensor. It's going to be far more efficient for your dollar than continuing to run being able to run extractive analysis every single day would add up. So I think that there's going to be that initial cost of purchasing the sensor, but then as you continue to implement that sensor, you're going to kind of see that benefit turnover over time.
Got a few more questions for you. Are you able to distinguish between the chlorophyll A that is in active living cells versus chlorophyll A that is not?
Great question. Yeah, so this sensor is specifically targeted to wavelengths alike that are targeted towards chlorophyll A. And you've got the degraded chlorophyll A that is what he mentioned is not active or not in living cells. It fluoresces at a different wavelength, so therefore we can kind of avoid the interferences of those accessory pigments and phaopigments based off of that specific excitation and emission spectra.
What do you think explains the lack of similarity of results across the 12 NERRS? And do you think that there might be another variable that you could use that would be similar?
Yeah, so I think some of that variability definitely has to do with the spatial location across the nation. I think that's really one of the great aspects about this project is a lot of times when people do this research looking at sensor values versus extracted values, it's just at one location. And that may show a great relationship. And when you extrapolate that amongst, you know, a larger, like we did across the whole nation, you see a lot more of that variability play out. And that may be due to a number of different things. You know, the community composition of the cells of the phytoplankton within the estuary is definitely a main driver behind, you know, any variability that we may see, which wasn't included in our study.
And a question related to the sensors that you're using. Do you work with the sensor manufacturer at all to share your findings related to the methodology on calibration? And are they improving their calibration procedures as a result of this project?
Yeah, so YSI, we've mentioned the research that we're doing. We didn't want to keep them too on board just because of potential conflicts of interest. But they have since, you know, I mean, they developed these sensors probably 6 or 7 years ago now, and people have been using them across the nation. This isn't the first chlorophyll fluorescent sensor that they've actually developed. They had one on their previous legacy SONs that we actually used, you know, 15, 20 years ago. But they are continuing, you know, they're adding statements within their manual saying that there may be inconsistencies between extracted values and sensor data, and they're realizing that there may be inherent inconsistencies that aren't accounted for just by calibrating to a rhodamine standard. So they do offer the option to actually specifically calibrate your sensor using a single species to give you a true linear relationship. But again, how that holds in, you know, a dynamic estuarine environment is to be investigated.
Great. Thank you so much, Silas.